Electricity is all around us. Um, and we often think of that as the electricity that's passing through wires, electricity of plugging something in. And while that's totally true, I think it's fairly limited as an understanding of what electricity is. In this unit, I want you to expand your understanding of what electricity is to also include things in the natural world. Because humans have been transforming other forms of energy into electricity since about the mid 1800s. But electricity um, is a natural phenomenon, and there it exists in the natural world. For example, bees and flowers. Um, Bees are able to sense this electrostatic field around the flowers to determine whether or not there's pollen available. It's incredibly cool. There's a cool video about that. Um, and there are certain animals that can detect electricity or generate electricity. Um, so that's one of the ways in which sharks hunt, for example. So while electricity absolutely is flowing through power lines, it's not the only form of electricity. And I'm hoping that within this unit, you're going to come to a greater understanding and appreciation of what electricity might mean. This first lesson is on atoms and materials, and you're going to be taking notes in your notebook while we do that. I would like for you to think about this. Why don't we make wires out of plastic? And you likely will tell me that electricity can't flow through there. It doesn't work. Plastic would melt. Those are all correct. Those are all accurate. Maybe not the plastic melting. It depends how much voltage there is. But you're correct that it wouldn't work. Do you really understand why? Like, what is going on? What do we mean when we say electricity doesn't flow through a plastic wire? So that's what I really want to get us at today. And that's something that I want you to keep this idea about why we choose certain materials for electrical conductivity and why things are made out of certain things. Your essential question is, what are subatomic particles and how do they behave in different materials? In order for us to really start with this, we need to understand what atoms are. So, atoms are the building blocks of matter. Just like we have the alphabet, 26 letters that allow us to form all the words that we say in English, there are 118 known types of elements, and different arrangements of these elements form literally everything in the universe. And so there's just so many different combinations of these 118 elements to create all of these different things that we have around us. Let's take, for example, this ant. If we were to zoom in on this ant, got to get even closer, right? We're down to the cellular level. If we get even closer, we know that this ant is made up of hydrogen, carbon, nitrogen, oxygen, among other things. And frankly, all of life on Earth is made up of those four elements plus some others, and that's what makes life life. So there's tons of variation within this. You are going to learn way more about atoms and kind of some of the other stuff in this lecture. You'll learn more about that in chemistry, but this is kind of just your taste of it and to give you enough information to understand what is happening when we talk about electricity. So we've got the atom. We want to understand subatomic particles. Now, just like this name suggests, sub means smaller than, smaller than. Okay. Okay. There's my smaller. There's a little e there. Smaller than, and atomic is atom. So when we talk about subatomic particles, we are talking about things that are smaller than an atom, parts of an atom. Okay, particles. So that's what we really mean by that. So you know how I said that there's 118 different kinds of elements, different kinds of atoms? Well, each of those 118 different kinds of atoms just have different numbers of only three subatomic particles: protons, those little p's there, neutrons, and these things that are buzzing around are called electrons. And each of these subatomic particles has a mass, meaning it's made of stuff, right? We should write that down. masses made of stuff. Probably would help if you write all the stuff. It's just really slow for me to write on the screen. So I'm just going to write stuff. And it has a charge. So by charge, we mean that it has, and this is going to go into kind of our electromagnetic field, that kind of a thing, a positive, a negative, or a neutral charge. 0. Okay. Okay, so while neutrons are important, for our purposes, we really only care about protons and electrons. These are the things that are going to help us to understand electricity. So first, we've got our protons. Protons have a lot of mass, and by a lot of mass, I really don't mean a lot of mass, but compared to the electrons, they have a lot of mass. They are always stuck in the nucleus of the atoms. Okay, and nucleus means the center. Where the heck is my? There we go. So nucleus is the center. They're not going to leave that center of the atom. They have a positive charge, +1 coulomb. That's what that big C stands for. So you can remember that proton positive, right? Electrons, on the other hand, have a teeny tiny mass. In fact, it's so small of a mass that oftentimes scientists, when they're performing calculations about like the mass of an atom, they just don't even include the mass of a electron. So it's like essentially 0 mass. Not totally true, but like basically 0. These electrons are able to orbit freely. They kind of are buzzing around free. I act like they're like a bug or something, but they are like moving around this center. Um, and they can even move from atom to atom. That part's really important because this aspect, that they can move from atom to atom, is exactly what we're talking about when we are talking about electricity. This is electricity. T. Okay. All right. It's no coincidence that the word electron and electricity start with the same letters. And electrons have a negative charge. So they have -1 coulomb of charge. Notice that protons and electrons have equal and opposite amounts of charge. Let's erase. Okay. All right. So with all of that information, we need to talk about the electrostatic force. And this is it feels a little tricky. But along with gravitation, the electrostatic force is one of the fundamental forces of the universe. And when we talk about electrostatic force, this is the force of attraction or repulsion of different objects to each other. So I'm going to talk about this kind of as if we're talking about magnets. And I don't want you to think that this is limited to magnets. In fact, it's a different mechanism, but I want you it helps to imagine magnets when talking about the electrostatic force for what I'm about to say. So the strength of the electrostatic force has a proportional relationship with the amount of sigma charge. Okay, sigma, really we just mean like total charge. Sigma is the symbol for it that you learned in the first unit. But I think that just thinking of it as total charge of each object and an inverse relationship with the distance between them. I'd like to first talk about this part. Proportional relationship with the amount of total charge of each object. All right, so let's discuss that thing right over here. If I have, let's say, a really strong magnet, right, and this magnet has is near another really strong magnet, right? These two magnets are going to be really hard to force together, right? Because they want to spread apart, right? So these both have really, really big charges. They have a lot of force that's kind of pushing them apart. If I have really weak magnets, right? Really weak magnets, these ones don't have a lot of charge, then their amount of force that they pull away with is not that much. You see what I mean there? So, like, it wouldn't be very hard for me to push these two magnets together. I could overcome that electrostatic force because the total charge of those is not very much. So, you can think of that as the greater the charge, oh boy, charge, the greater the charge, the greater the force, the electrostatic force. That's that proportional relationship. If I increase the charge, I'll increase the force. Now, I'll take a different color here. I know that this is sloppy. Hopefully, you're taking, better notes. An inverse relationship with the distance between them. All right. So let's take our same magnets here, and we have, one magnet that's here, and the other one is, let's bring it really close, right? I bet that you have felt that. I'm going to say that both of these have the same. Let's make both of these have different charges, right? No, we'll make them both the same. Keep it the same. Good deal. So since these ones are so close together, your ability to try to press them together is really, really hard because they have a lot of force that's pulling them apart, right? If we bring those same two further away, they don't feel the charge of the other one very well, right? And so they're not going to have nearly as much of a force. It's pretty easy to hold those two at a distance, and they're not going to come slamming to, or excuse me, they're not going to want to fly away from each other. All right, so that's sort of inverse distance is if you increase the distance, you decrease the force. That is what we mean by that proportional and inverse relationship. So those words that you have on your screen here is kind of feels like a more complicated way than just saying this. All right. So whether or not the electrostatic force is going to bring objects together or send them apart is based off of the charges of these objects. So opposite charges attract toward each other. Opposite charges is an example. Oh yeah, I'll just use the focus here. Opposite charges would be this one and this one. So a positive and a negative, they want to come together. If they have the same charge, then they repel. So that negative and a negative want to move away, positive and positive want to move away. And again, you can think of this with magnets. It's that kind of a thing, but please don't think that this is just limited to magnets. This is a different thing. But you're welcome to think of that. It helps to imagine what's going on by thinking of magnets. All right, conductors and insulators. Conductors and insulators are types of materials. And we have a pretty good idea of the types of materials that will conduct electricity, like electricity can flow through them, and the ones that electricity can't. So, conductors, metals, right? Salt water is a conductor. Insulators are our plastics, our woods, that kind of a thing, where we know that if we were to hook them up to a battery and a light bulb, the light bulb is not going to turn on, the light bulb will turn on. Okay. That's a pretty like elementary, middle school concept. What I want you to understand is what is it about conductors that allows electricity to pass through? What is it about insulators that allows it not to pass through? All right, so talking about those subatomic particles, since protons are stuck in the nucleus in the center, the number of protons in an atom stays constant. This number determines which element the atom is and also the physical properties of that atom, such as electrical conductivity. Basically, it takes 9 protons to be in a fluorine atom. It takes 3 protons to be a lithium uh, element. So if I were to take away a proton, I turn fluorine into oxygen. Like I change literally what it is. And you are going to learn about what it is about these protons that makes something conductive or not. You're going to learn about that in chemistry. Right now, you just need to kind of trust that these protons do affect whether or not this element of fluorine is conductive or this lithium is, right? Conductivity is how easy or difficult it is for electrons to move from one atom to another. Okay, that's our idea. How easy it is for electrons to move from one atom to another. Might help for you to circle that, underline it. How easy it or difficult it is for electrons to move from one atom to another. That's conductivity. If it's easy, it's conductive. If it's hard, it's not. So here we have this sodium atom and this chlorine atom, and it's really easy for the electron to move from there to there. Sodium and chlorine make up salt, and salt water is really conductive. So there's kind of our example of, how an electron is moving away from its nucleus to somewhere else. So an insulator is a material with low conductivity. This is something you could safely stick in a light socket. You can stick a plastic fork in a light socket. You'll be fine. All right. Um, in fact, that's why we cover, or why I cover with a young child, my all of my sockets with these little plastic things, right? So that because that's safe. I'm not going to get electricity passing through there. The nuclei of the atoms are hanging on tightly to their electrons. The electrons do not want to move away from the center of the atom. They can move around inside the atom, they can like orbit, but they will not escape away from those protons. Here's an example of what that might look like. So imagine that this is a piece of plastic, right? And I've got each of these different lines represents like one of the atoms that is in this sheet of plastic. The electrons are allowed to move like around this nucleus, okay? But they are not going to travel to another one of those nuclei. So if I were to hook up, let's say that I took a wire and I hooked it up right here to this part of the plastic, and I have my battery here, right? Here's my battery, and I have a little light bulb. Oh boy, this is gonna take a while for me to draw. There's my light bulb. Oh boy, right? And I connect that to this side. This light bulb is not going to turn on. It is not going to turn on because these electrons are stuck around their nucleus. They are not traveling and kind of bumping into each other, and we'll talk about that. But they are not moving across these lines. They are just staying right there. So there's no real communication between this electron and this electron. So I don't have a circuit here. I don't have a loop. So some examples of this would be wood, rubber, plastic, to name a few items. Most fabrics are insulators. Okay. Let's compare that with a conductor. So this is something that you shouldn't stick in a light socket, right? I said that you could stick a plastic fork in. Please do not stick a metal fork in. You'll get 120 volts of electricity right at you. These atoms share their electrons. So the electrons can move anywhere within the material, and they can easily even move on or off that material onto another conductor. All right, so if I have like one piece of metal and another piece of metal next to it, and those two pieces of metal are touching, those electrons can move over. So we've got that same sort of idea where we have, let's call this like a sheet of metal, and we have all of these electrons, and these electrons are allowed, like this electron can just move anywhere along here, right? It's not restricted in the same way, right? It's not restricted in the same way that the other one was. Okay, right? Can go anywhere. So I don't know that I want to draw it on here, although I think that it could be good for you to draw it on there. It's just going to take me forever, but we got our wire, we got our battery. I'm going to draw kind of more of a circuit-like battery, right? We have our light bulb. All right, I guess I'm drawing it, right? And now, because those electrons are free to move and they can kind of bump into each other and bounce between these different atoms, now we get a light bulb that turns on. Great. Okay. And with that, we are talking about some examples. Metal is a great one, and salt water. Not necessarily fresh water. Fresh water is not a conductor, but salt water is. Okay, so those are some examples. All right, I know that's a doozy. Just to debrief this, to revisit our essential question, the question is, what are subatomic particles and how do they behave in different materials? Subatomic particles are protons and electrons and neutrons, but we don't really care about those. Protons have a positive charge and a larger mass. They stay in the nucleus of the atom. Electrons can move around freely. They have a negative charge and a small mass and exist outside of the center of the atom. The different materials in electric force are conductors and insulators. We have two major categories of that. In conductors, electrons can move freely through the substance. And in insulators, electrons stick close to their nucleus. They are harder to move. So in both conductors and insulators, protons will stay in the nucleus and within the original substance. All right. With that in mind now, I'd like for you to try to rephrase this into your own words to answer the essential question.